Okay, this is number 5 in section 3.3 of your book. And it says, determine whether x equals 0 is an ordinary point, a regular singular point, or an irregular singular point. And if it's regular singular point, then find the exponents of the differential equation at x equals 0. So this is our given differential equation, and we want to write it in our standard form. So I'm just going to go ahead and divide by x times 1 plus x to actually, well, we can split it up, that's fine. You can write it as one whole fraction bar if you'd like. Okay, well that's just going to be 0, but let's just go ahead and write it in. Okay, so we're left with y double prime plus, and I'm going to go ahead and write it as 2 over x times the quantity 1 plus x, y prime plus, and then we have, well, this is nice, this is gone, so we get 3y all over 1 plus x, and then we can actually, I mean, the y is fine there, I just want to write it in the middle, equals 0. So this is nice because this is our standard form. We can easily see our p of x and our q of x. And now let's take the limits. So we're going to find, so we're trying to determine, so p naught, and that's a small p naught. So, oh, okay, looks like a cap, but that's my little p naught. And we want to take the limit as x approaches 0 of our p of x, which is x times capital P of x. So this is just x, right, a factor of x times my p of x, which is this guy right here. And so we have, well, let's go ahead and write it out. So 2 over x times 1 plus x. And, well, let's just go ahead and work this one out, right? These guys are 1, so we're just left with, and actually, let me go ahead and work vertically. So we're left with the limit as x approaches infinity of the following function. Now you can graph this function if you like. It's a rational function, the asymptote's at -1, but remember when you first started learning about limits in Calculus 1, right, the easy approach was first to try direct substitution. Whoops. And if I substitute 0 for x, I get 2 over 1 plus, right, 0. And, well, that just gives me 2 over 1, which is 2. So there's, I mean, at x equals 0, this rational function is fine, right? Nothing bad is going on. So just geometrically what we're talking about here. So again, this is just a sketch. So 2 over 1 plus x, so that's really x plus 1, so it has a negative. My asymptote is at, let me maybe draw a different color here. So, right, if you graph this right from college algebra, your graph looks something like this. So, let's do it in, I don't know, let's do it in purple. It looks something like this. Right, and notice that at 0, right, as the limit is approaching 0, I mean, well, actually, this is a really bad graph. Let me go ahead and, there's my eraser. It's actually pretty bad. Let me get my green. Okay, so at 0, right, we actually, if I give you, if x is 0, this point here is actually 2. So there's, I mean, we do get a value, right? It's when x is approaching -1, right? We get 0 in the denominator, and that's undefined, right? It grows really, really rapidly. So there's no problem there. And let me go back to this purple. So remember, this is right. It's getting closer and closer and closer to this asymptote, but it never actually touches. And similarly, here. Okay, so that's, the limit is 2, right? It definitely, it exists. So let me get my white here. So obviously the limit is finite, right? Or it exists. So now let's do the same thing for Q naught. So Q naught from our last video was the limit as x approaches 0 of little q of x, which is just x squared times capital Q of x. And what was our Q of x here? It was, I'll just keep doing blue here. They're not obviously the same, but so I have 3 over 1 plus x. And so the limit as x approaches 0, 3 over 1 plus x. And again, this is just your first year of calculus. You're just evaluating limits. Let's see. So we're left, okay, so the limit as x approaches 0, we can definitely, I mean, we have this 3 here, but we can just take it out as a constant. So I'm going to just go ahead and write it out. So times x squared over 1 plus x. And here, if x approaches 0 again, nothing bad is happening. I mean, we have 3 times, let's just write it like this, 0 squared over 1 plus, okay, 0, which just gives us, right, well, I mean, this is 0 divided by anything is going to be 0. So, well, 0 over 1, right? But all this is 0. So, I mean, 0 is a finite number. So the limit does exist, right? We get a finite number. So we know the limit exists. So we have, so let's just kind of summarize. So my P naught, small p naught, was 2, and my Q naught is 0. And if you look at, hopefully you've seen the previous video, I said if P naught and Q naught are both 0, then our x equals 0, it may be an ordinary point. Okay, that's not the case here because they're not both 0, so that's out of the question. And I said otherwise it will be either a regular singular point or an irregular singular point. And we have limits. These are limits. They exist. So therefore x equals 0 is, so thus x equals 0 is a regular, right? Because we're talking about singularities, and there's special types of singularities, regular and irregular. So regular singular point. And I think that, I mean, that's pretty much it for this part. And again, remember, since the limit exists, our P of x and Q of x, our little p of x and q of x, have Taylor series expansions. So the next part is, if it's a regular singular, which it is, find the exponents of the differential equation. So we're going to use our indicial equation, and our indicial equation is, so our indicial, so I was going to write it down. So indicial equation, and I'll go ahead and elaborate on this in just a bit. Okay, so our equation is r times this quantity plus p naught, the p naught that we just found, r plus q naught equals 0. So, I mean, there's our p naught, so we can just insert it, and there's our q naught, which is nice, it's just 0. So if we substitute these values, we obtain, let's see, so we have r times this quantity plus 2, that's 0, so that's very nice. And then this all comes back to college algebra, really. I mean, this is just a quadratic equation, right? If you distribute these guys, we get r squared minus r plus 2 equals 0. And for the previous section, you guys were factoring quite a bit. So we have, let's see, I think I made a mistake. Oh, I forgot my R here. That should be an R. All right, I just wrote my additional equation incorrectly. So now we are left with, oh, actually even easier. This is R squared plus R equals 0. And then, right, we can factor out an R. Right, therefore, the possibilities are 0 or, well, let's just call it, it's R equals 0 or R equals -1, but we can call this R sub 1 and R sub 2. So these are the exponents of the differential equation. Let me just go ahead and write that down. All right, so let me erase that. So thus R1 equals 0 and R2 equals -1, right, are the exponents of the differential equation at x equals 0. And this section, it goes into the Frobenius method, which again I haven't talked about, but just a quick, because we're going to be obviously using the Frobenius method. And if you look at Theorem 1 on page, make this a little bit bigger. So Theorem 1 on page 225, there's a Frobenius series solutions, and there's special types of series solutions. And basically, for now, I want you to understand that, so we have our R1 and our R2, and I'm looking at, let's see, I'm looking at, well, the very first part. So it says let R1 and R2 be the real roots. Well, these guys are definitely real roots, right? They're real numbers. And R is strictly greater than R2. Yeah, R1 is definitely, well, we know it's not equal to, but, right, 0 is greater than the -1. We have our additional equation, so that tells us that there's a special series solution, excuse me, written as the following. So we have y1 of x equals x to the r1. Well, our r1 is, let's see, let's pick a yellow here, right? This is my r1, which is 0, times our series here. So there exists a series solution of this form, right, that corresponds to this R1, and specifically, this is the larger, right, this is the larger exponent value. And again, I'm going to go into more detail on this, but I'm just using Theorem 1, specifically Part A, right? This is really just equation 18, where R1 is 0. So that is number 5 in your book.